Hello and welcome to this fourth video in a series of videos on factoring. If you're watching this video, you should have already seen the video on the overview of factoring, as well as the instructional videos that show you how to factor expressions using greatest common factor, also known as undistribution, as well as differences of two squares. In this video, we're going to continue learning a new method for factoring, and that method for factoring deals with perfect square trinomials. So I'm going to continue to work through these green methods through these videos, and right here is perfect square trinomials, so I'm going to go drill down inside it and try and create a submap for this concept map and try to demonstrate this skill for you. Much like differences of squares, differences of two squares, perfect square trinomials is a pattern-based factoring. There's just a model that we use to generate the factoring answer from the problem when it's given in a certain form. Okay? We'll talk about some prerequisite skills here. Okay? They're very similar. You've seen these before with differences of two squares. You need to be able to square root a perfect square. You need to be able to identify a perfect square. And as always, when we talk about factoring, it's important to be able to have a skill of foiling so that you can, in fact, check your answers by just multiplying out your product that you create to make the factoring. Okay, and then hopefully as I also move through this, we'll try and show you a list of steps here that you can rely on pretty steadily for factoring perfect square trinomials. Okay, let's first start by exploring this model, this special pattern that I referred to. Okay, so we have here a perfect square trinomial, and they all have this particular structure. The first term is a perfect square. The last term is a perfect square. Now the middle term is a little bit of a curveball. If we see where it says 2LR, they don't all necessarily look like they have a 2 in them per se when you go to identify them. But what this says, this term here that says 2LR, it says that the middle term is 2 times the product of the square roots of the first and third terms. I'm going to take a second and write that for you. Now, I paused the video so that I could write that because it really is a mouthful. I think it's a good idea to pause the video, read it a couple times, and try and see how this middle term is actually what I've written here, because they are, in fact, identical in terms of their nature. Again, we see that the 2 times part is given by this 2. The product of the square roots, well, the product of the square roots is the L and the R, and the first and third terms this refers to that the L is the square root of the first term and the R is the square root of the third term. So it's a bit of a mouthful, but if you get to practice saying it, it's going to make sense. You have to say it slowly and surely and try and find the reading in this middle term while you're doing it. So we're going to develop that idea as I go to identify the problems as perfect square trinomials when I do the examples. Okay, so for now though, let's just verify this pattern. It shouldn't come as any shock that when I FOIL this out, I'm in fact going to get L times L is L squared. L times R is LR. R times L can be written as LR again because multiplication is commutative. I can change the order. And then we've got R times R is R squared. Okay? So we see that we have like terms in the middle, and then I can in fact say that that's L squared plus 2LR plus R squared. And we do in fact see that that is the original expression. So this and this have to be equal. Okay, just a very quick review about identifying perfect squares and square rooting perfect squares. Identifying a perfect square should be relatively simple. The perfect squares are, excuse me, wrong tool. 1, 4, 9, 16, 25, 36, etc., etc. And you should have them at least memorized up to 144, which is 12 squared. So the coefficient needs to be one of these numbers. The exponent just has to be even. So for example, something of the nature of 81 x to the 6th is a perfect square because 81 is from the magic list and 6 is even. Okay, square rooting perfect squares, we'll say I took my 81 x to the 6th. If I were to square root it, I would square root the 81 and get 9, and square root the x to the 6th by cutting the exponent in half. So the only thing here that's out of the ordinary you have to remember is halve the exponent when we're square rooting. Okay? That's pretty much the predominancy of what you need to remember. Square rooting a coefficient is going to come naturally to you. Okay, so let's take a look at some examples and some steps I've written out for you. Okay, so factoring a perfect square trinomial. As always, in all factoring, I look for the step 0, GCF, factor with GCF if possible, greatest common factor. Also, we joke around and say that it's got to come first. That's what GCF sort of means too, because we always look to do GCF first. Then confirm that it's a perfect square trinomial. Well, that's where I'm going to show that it lives up to this model of L squared plus 2LR plus R squared. Okay, then it says use the special pattern to write the factoring. The special pattern is just the quantity of the sum of the square roots times the quantity of the sum of the square roots. And it makes sense because if I'm getting a perfect square trinomial, I'm actually writing something times itself, which means I'm squaring it. Now, just a quick caveat. You're not always going to get a plus plus when you factor these. Sometimes you'll get a minus minus when we do this, and that just depends on the middle term. If the middle term is plus, you get 2 pluses. If the middle term is a minus, you're going to get 2 minuses. Okay, so let's kick into gear here and do some of these problems. So we're asked to factor x squared plus 20x plus 100, and the first thing I look to do is see if there's a GCF. Well, the x doesn't appear in every term, so that's not a GCF concern. And what is the GCF of 1, 20, and 100? It's just 1, so I don't worry about that. There's really no GCF. Now I just verify that it's a perfect square trinomial. It's obviously not a difference of 2 squares because it's 3 terms. Okay, so let's see. We have that the first term is a square and its square root is x. We have that the last term is a square and its square root is 10. Their product is 10x, and if I double that, I do get this 20x in the middle. So the pattern checks out. So the only thing I need to do is write 2 quantities. The middle term is a plus, so I'm going to write 2 pluses. And then the only thing I need to do is take the square root of the first term. So the square root of x squared is in fact x and x. And the square root of the last term, being 100, will be 10 and 10. You could take a moment and FOIL that out and see that you in fact do get the original expression. Okay, I hope you appreciated the fact that it seems like it's more work to verify that it's a perfect square trinomial than actually do the factoring. That's a little bit what's weird in these problems. Once you know it's a perfect square trinomial, you're only going to use the square roots of the first and last term, so it's pretty easy. But again, the trick is knowing it's a perfect square trinomial. Okay, so where does that leave us on this next problem? Let's see if we take a look at y squared minus 18y plus 81 and look for a GCF. Well, there's not a y in every term, and the GCF of 1, 18, and 81 is just a 1, so there's not a GCF to speak of. So let me verify again if this is a perfect square. Well, trinomial, if it is, the first term is a square, and it is. Its square root is y. If it's a perfect square trinomial, the last term is a perfect square, and it is. Its square root is 9. Their product is 9y. When I multiply it by 2, I get 18y. Well, that's fine that it's negative 18y because it just means that when I set up my factoring, I won't use two positives. I'm going to use two negatives. Okay? Or I should say two subtractions versus two adds. So now that I know it's a perfect square trinomial, I factor y squared into y and y by taking its square roots, and then I factor the 81 in its square roots of 9 and 9. Okay? And again, if I took a moment to FOIL that back out, I would get the original expression. Now, just before I go into these next two examples, there's something you want to also see here. Many times, these answers will not be written as repetitive factors, where you see it's the quantity x plus 10 times the quantity x plus 10. A lot of times, they'll be written as the quantity of x plus 10 squared. Or in the case of the next example, it will be the quantity of y minus 9 squared. Okay? Both are legitimate answers in terms of the formats. This one here, where it's written as a square, it has many applications where we prefer to write it that way. But for now, just realize that either or is an appropriate answer. Okay, so let's move on to a couple more examples. Okay, this one's a little different looking because if we see here, the first coefficient's not 1 anymore. Okay, so let's take a look if we can factor with a GCF. And there's not a y in every term, so there's no y GCF. And 25, 20, and 4, their GCF is 1, so there's not really a greatest common factor of note. So let me just, again, sort of try to mentalize around if this is really a perfect square trinomial. And we see here that the first term's a square, whose square root is 5y. The last term's a square, whose square root is 2. Their product is 10y. And if I double that, I get 20y. And it's fine that it's negative 20y, because that just means that as I go to use this special pattern, I will use two minuses. And then again, I will square root my 25y squared and get 5y and 5y. And then I will square root my 4 and get 2 and 2. This is a completely legitimate answer, the quantity 5y minus 2 times the quantity 5y minus 2. Or again, you could say 5y minus 2 all squared. Okay? Now in this last example, I tried to show you that sometimes you have to do a greatest common factor. One thing I want you to notice right away here is this 27 and this 75. You'd look at this and say, well, that's not a perfect square trinomial. Well, let's let it develop here and see what we get. So factor with GCF if possible. Well, what is the GCF of 27, 90, and 75? Well, I believe that it's 3. So I'm going to take a GCF of 3 out of this problem. And if I look back again, there's not an x in each term, so it's just 3. So, again, if you remember your GCF maneuvers, it's divide by the GCF to find the other factor. So we're going to get 9x squared minus 30x plus 25. Okay, well, it seems like it's a GCF problem. But if you continue to look at it and look at this factor here, we see that it has 3 terms. We see that the first term is a perfect square, whose square root is 3x. We see the last term is a perfect square, whose square root is 5. Their product is 15x. And when I double that, I do get 30x. So this part that I've highlighted here is a perfect square trinomial. Well, I'll set up my two quantities with minus signs, but more importantly, you cannot forget to bring down this 3. It's part of the expression, so what I'm going to do is make sure that I put my 3 there. So it's going to be 3 times these quantities. And then I just take the square root of 9x squared, which is going to be 3x and 3x. And then I take the square root of 25, which is going to be 5 and 5. This is a completely legitimate answer. And if I multiplied it all out, I would get the original problem. You probably suspected also that I could write 3 times the quantity, 3x minus 5, all squared. So, I hope this demonstrated this process of factoring perfect square trinomials. I'm going to take a second to get a screenshot here of my steps, and then I will paste that into the flow chart. Maybe I can shrink that down just a little bit. Okay, so again, the steps are factor with GCF if possible. Confirm it is a perfect square trinomial by identifying that the first and last terms are perfect squares. And again, that middle term, that it's 2 times the product of the square roots of those perfect squares. Okay, just a quick review here. When we're identifying a perfect square, you need to know that the exponent must be even. The coefficient needs to be from that magic list of perfect squares. And when you're square rooting a perfect square, the exponent is just cut in half. So enjoy. You might want to attend to some practice problems and try and master this skill before you move on to the next type of factoring.